Hello, welcome to my channel. Please subscribe and leave a comment. Go through the description and follow the links for more of the videos. So last time we looked at surds, looked at an introduction on surds. So now we are continuing the definition. If I have the root of m, if root m is such that m can be expressed as a product of a perfect square and an integer, then we can say that root m is reducible. What do I mean by a perfect square? A perfect square is any number that can have a square root. Can be, for example, if I have root of 4, that one we can get the square root of root 4 as 2. Therefore, 4 is a perfect square. So if I have root of m and I can express it as a perfect square, that is a product of a perfect square and another integer, p is a perfect square because we can get the square root of p. If I take the square root of p, it means that this 2 is going to cancel with the root and we are remaining with p. Then 2 is an integer, cannot be, its square root cannot be gotten. Therefore, it is an integer. Root of m being expressed as a product of a perfect square and an integer, it means that m is reducible. Therefore, that's the concept we are going to use for all reducible surds and how to go about reducible surds. So this is what I was talking about. P squared can be expressed as a root. The square is going to cancel with the square root. Therefore, we remain with p. So p is a perfect square. And since we can't get the square root of 2, then 2 is not a perfect square. It is just an integer. So if I take the square root of p, it means the square is going away and the root sign is going away. I remain with p, and then the root of 2 cannot be gotten. So the final answer is p root of 2. That's how we go about reducible surds, and that's the concept that applies to all of them. If any number can be expressed as a perfect square and another integer, then that one is a reducible surd. So let's look at some examples. So for examples, we're saying evaluate the following. I have the first one as root of 12. 12 can be expressed as product of a perfect square, that is 4 and 3. We can easily get the square root of 4 and we cannot get the square root of 3. So this is a product of a perfect square. 4 is a perfect square and 3 is just an integer. If I multiply these ones, I come up with 12 again. So what do I get when I get the square root of 4? Square root of 4. So from the second rule of surds, these ones can be separated, each in its own root. Root of 4 times root of 3. I'm aiming at getting the root of 4. What is the root of 4? The root of 4 is 2, and I can't get the root of 3. So the final answer is 2 root 3. Then the second example, I have the root of 27. 27 can be expressed as a product of a perfect square and another integer, that is 9 times 3. I can easily get the square root of 9. So from the second rule, I can separate these ones, each into its own root. So square root of 9 times the square root of 3. What is the square root of 9? Square root of 9 is 3. So 3 has no square root. So it is just an integer. It is just a real number. Therefore, we cannot easily get its square root. So the final answer is 3 root 3. I leave it in surd form. Then the other example, the square root of 175. This one can also be expressed as a product of a perfect square and another integer. So 25 we can easily get the square root of 25, and 7 has no square root. So that's what I mean by a perfect square and another integer. So this is the same as the root of 25 times the root of 7. Remember, from the second rule of surds, we can easily separate these ones, each into its own root. Root of 25 times root of 7. So I can easily get the root of 25 as 5, and I cannot easily get the root of 7. So the final answer will be 5 root 7. So that's how we go about numbers concerning reducible surds.